I'm a civil engineer who's interested in environmental flows, geophysical flows in general, and of course we are much motivated by oceanic situations such as the overturning that you're seeing here. So I want to keep things simple and focus on shear, so vertical shear of horizontal velocities, and stable stratification. So I'm gonna, like Alexis, I'm not gonna worry about double diffusion, convections, or rotations in this talk, just to keep it simple. So a few concepts that I want to go over before I delve into the details of the talk. So I'm interested in layering, right? So when we talk about layering in oceanic flows, I think at least we can think of layering of density. So Phillips mechanism, you know, the left-right flanks that Alexis has talked about. So in this talk, right, I will rather focus on momentum, right, which is kind of motivated by field measurements like this. So you are looking at a depth of a few hundred meters in the vertical, and so time axis that shows about half a day, and plotted in color is some anomaly of the shear squared to the background state. That's why you can see actually negative, right? So it's because it's normalized to be zero mean here. So, and if you look closely right here, right, you see layers of shear, right? This, and maybe it has a vertical length scale of maybe 5, 10 meters, and it persists for a long time, right? Maybe a couple of hours over there. So, and the authors of this paper suggest that this could be internal wave packets that's propagating through the sites. And I think it's a tall order for any oceanographers to say for sure what they are. And I'll actually take an alternative approach. I will think of negative viscosities in the ocean, right? So whether it's instabilities, it's waves, it's mean flows. I'm going to try to quantify the negative, the effective viscosities in the flow, right? So normal viscosity, like molecular viscosity, will tend to smooth things out. If you have negative ones, I'll try to go with a stick because I don't think this highlighter works so well. So if you have negative viscosities, it's going to try to make layers. So we'll see if we can quantify that using a numerical simulated data set. And the next concept, which is self-organized criticality here. I think for physicists in the broad community, right, this is not a new concept and it's been used quite a bit. But for ocean mixing community, it's really introduced in the sort of the last few years of the past decade. So if the best way to think about it is through this sand pile experiment, right? So you're releasing sand from your hand and making this conical shape of sand pile right here. So as you add more material to the pile, your slope is going to steepen, right? So once you exceed the angle of repose, right, you're going to have some slides, some avalanches, right, which will bring the slope back to the subcritical state. And as you add more sand, the new cycle starts. So, and the argument here is, does ocean turbulence make it sand piles, right? So, and there are a few theories around to explain SOC-like behavior in ocean turbulence. And I'm going to show you right here. So the first one is done by Bill Smythe and co-workers. So you're looking at the 4 panels of, again, ocean measurements here. Panel A, first one, you're looking at the mean velocity profile for, again, 120 meters. Second one is the heat flux. Third one is the most interesting one. You're looking at the red is the mean shear. Okay, so it's taking some average of the vertical shear of horizontal velocities, so this quantity right here. And you're looking at the stratification profile, so vertical gradient of mean buoyancy. So if you take the ratio of the green and the red, right, you're getting the gradient Richardson number, right, which the authors plotted in the last column. And what attracts the column, the author here is the number, the values of gradient Richardson number actually sticks to the 1/4 number for a significant distance over the profile. So that motivates the author to say, do we have an angle of repose in the ocean that's Richardson number 1/4? And the authors actually provided more evidence to this argument. they look at the conditionally sampled dissipation rates, right? So how active the turbulence is. So, and they selected 2 years to show this, two data sets to show this. So the red one here, we are looking at the lower 75% in terms of dissipation rate. So this is the less active regions in the ocean, and you're looking at the PDF of RI. So, and for both data sets, right, you're seeing a quite broad distribution of that quantity. Okay? And if you look at the top 25% in terms of dissipation instead, which is the blue curves right here, blue distributions here, you see that peak almost spot on 0.25. Okay, so it seems like ocean turbulence is trying to cluster around that 1/4 magic number, at least for the most active parts of the ocean. And some explanation was provided for why you observe this kind of phenomena. This is the phase place that the authors choose to work in. So vertical, you have a Richardson number. So of course, anything beyond 1/4, you are stable, right? That's why anything above this line, quadrants 1 and 4, you see the turbulence decays because it's stable. And this is the equatorial undercurrents, right? So everything is forced by a surface wind here, which is quite steady in this scenario. So if you start with quadrant 1, and the wind is acting at the surface, your shear is going to increase. Okay, so you got one forcing that's trying to increase shear. If you increase shear, you're going to bring down Richardson number. So you're going from quadrant 1 to 2, right, as your Richardson number drops. Now you're in an unstable zone, right? So you're going to have shear instabilities, and you're going to make turbulence. So as your turbulence grows, your TKE will grow as well. And at the same time, right, you're making radial stress and buoyancy fluxes. So you're trying to smooth out the gradients by turbulence. Okay, and the result, of course, your mean profile will have less shear in it, and your Richardson number tend to grow again. So that's what happens between quadrants 3 to 4, and you're stable again, your turbulence decays, and that starts the new cycle. Okay, what I like about this cycle, right, is you can actually find all the counterparts of all elements in the Senpai experiments here. So for ocean turbulence, the sand source is played by the wind. Okay, it's like a main forcing that brings your flow from unstable to stable. So everything critically depends on the wind right here. And your mixing events, right? So your radial stress or buoyancy flux correspond to the avalanches, right? So you got some events that will bring you from stable to unstable. Okay, so that's you see the correspondence here, and the angle of ripples here is just the critical state of Richardson number quarter. So you see the nice story right here, right? Everything has its counterparts. Okay, so this is the first mechanism of SOC, and it depends on forcing. The second one, so Alexis also mentioned this. I'll be quick here. So there are really 2 scenarios of mixing, right? You can think of if you have weak stratifications. Let's say we start with a weak interface here, and you can create some intermediate density fluid here, and everything's going to overturn, and you got overturning mixing, right? So this kind of scenario, mixing is very transient. It doesn't last for a long time. Whereas if you're in a scouring scenario, you have a sharp interface to start with, it won't overturn, and the mechanism of mixing is by this eddies taking material away from the interface. And to show you animation from my postdoc work here at Dent, you're looking at a initially sharp interface embedded with some noise or turbulence to start with, and you actually achieve this humble wave state, which again, right, the pair of vortices emerge on either side of the density interface. You take the material away instead of mixing it up, and you keep that density interface very sharp. And I should mention that you don't get this kind of a state if your Prandtl number is not this high. So the Prandtl number for heat in water is 7, and for salt in water is 700. So we made this fictitious fluid that has Prandtl number 70, and we get to this state, right? And this, because we need to resolve the Batcher scale, it's really expensive to run computationally. But if we change the Prandtl number from 70 to 7, this interface, this flow, will actually laminarize because molecular diffusion happens very quickly, and it's going to diffuse that interface in no time, right? So if you want to have squaring mixing, you really need your Prandtl number or Peckley number to be large enough. Okay, so people have looked at, Silentford et al. Has looked at this PDF of Ri in different types of shear-driven turbulence. And the striking thing they found is if you are working with Kelvin-Helmholtz-like shear instabilities, your Ri will not center around the quarter magic number. But if only in that Humboldt wave regime, you get this sort of clustering behavior in terms of Ri. So in order to get SOC using this mechanism, you better make sure that there's a sharp interface and Humboldt wave instability in your flow. So that essentially summarizes what I just said, right? So two mechanisms here. First one depends on the wind as the forcing. Without the wind, right, you won't have that cyclic behavior. And second one depends on this sharp interface and maybe a high Prandtl number. So, and what these two theories have in common is the same critical state, which is the Miles-Howard quarter, you know. And the question I'm asking here, you know, if we don't have interface, if we don't have forcing, can we still get some SOC-like behavior? So if it does, then that means this SOC behavior is a generic property of turbulence, and it's not dependent on any forcing or some particular initial condition. Of course, to test our hypothesis, we want to look for a flow that doesn't have a forcing and doesn't have a sharp interface. And the flow I'm looking at here is stratified wakes. You know, in the lab, that's what you just have to tow something in a stratified flume, and that's sort of the dye pattern that you see afterwards. And in simulations, of course, it's really hard to compute around the sphere, and you just initialize a tube of turbulence and let it go, right? So, and I should say that in the experiments or in the simulations, I'm using a constant buoyancy frequency, right? So I'm not making any interfaces in there. And if you look at this flume pictures, right, so you're looking from the top into the flume, looking at the dye, right? So initially, so time now here is normalized by the buoyancy frequency. So initially, you see some small scales that's over there. And because of the confinement effects of stratification, right, things are harder to be transported in a vertical direction. The wake would collapse. Okay, as it collapses, it's going to grow into pancakes. Okay, so the horizontal scales will grow quite quickly, but the vertical scale of that wake is going to almost be locked. Pretty much the same as in the three pictures, right? So as you go over, as time goes on, right? So the aspect ratio of these structures will grow even more extreme, right? So really large scales in the horizontal, thing in the vertical. And since we're looking at layering here, I'm really looking into the thickness of the pancake, right? Even within that very thin pancake, can we still get layers? And you can see some animations here. So I'm looking into the flume again. So I'm looking at horizontal slice of the numerical simulation, and the quantity you're looking at is the vertical vorticity, so vorticity normal to the plane, and I'm comparing two Reynolds numbers here. So 5,000, pretty boring. You just see lots of pancakes over there, very smooth. And for this larger Reynolds number, you see seems like noises that's emerging on the pancakes, right? And you clearly see some scale separations here. Looks like there are some secondary events that's happening here. So let's see a bit more details into these structures. So I'm adding a new Reynolds number here, which is even larger. So upper panel, I'm showing you the same thing, so vertical vorticity on the horizontal plane. And lower panels, I'm showing you a side view. So I'm looking at the vorticity out of the plane. And as you can imagine, right, so this quantity is going to be dominated by vertical shear. So if the Reynolds number is not big enough, you see quite diffused, quite wide layers right here. So that's because the flow is actually growing viscously, right? So not very interesting right here. But for the larger two Reynolds numbers, you see those layers? And those are taken at the same time in a simulation. For the higher Reynolds numbers, you still see some disturbances that's in that layer. So first of all, we show that layering has happened in terms of shear. And higher Reynolds number, you actually see more secondary events right here. Okay, so even more pictures kind of showing you the same story. So low Reynolds number, the vertical scale of the wake is growing viscously, quite smooth, quite slow. And as you increase Reynolds number, you see that layers in terms of shear. And the highest Reynolds number, you still see lots of turbulence at a very late time in a wake. Okay, so I don't know why this becomes so small. So we have a snapshot of this vorticity plot here, and what I wanted to show you in this is a regime diagram, right? So just take my words for it. In the horizontal axis, as you go to the right, you are having less viscous structures, right? So I'm plotting the Reynolds number for the horizontal eddy, right? So and in the vertical, I'm plotting the inverse of Froude number. So in this top right corner of that regime diagram, you have this regime called the strongly stratified regime, and in that regime, right, you can show using scaling arguments that the layers that's going to emerge from the flow is going to follow this scaling right here, and we tested that to be true. So we know, we are confident that this is in this magic SST regime, although you don't really see it. That's okay. So we're going to test our hypothesis here, right? Which is within the SST regime, the flow is going to self-organize to reach the same kind of SOC behavior that people have observed, i.e., right, the RI is going to cluster around a quarter. So this is a DNS data set, right? So it's really well resolved. During my PhD, I have done even higher Reynolds numbers, but that's LDS data set. I decided to use a different one. And it's quite a computationally expensive study. So I'm going to focus on one data set, and I'm showing you some time series here. So just before I do that, there are some important length scales and dimensionless numbers I want to introduce. So Kolmogorov scale needs no introduction. So Ozmidov scale depends on dissipation rate and the buoyancy frequency. Okay, so there's scaling arguments about Ozmidov scale, and it's sometimes considered as the smallest scale that can feel the effect of turbulence or feel the effect of stratification. I'll come back to that. REB, right? So if you write it this way and using the definitions here for Kolmogorov and Ozmidov, you can show that REB is actually the ratio of Ozmidov over Kolmogorov. So if your REB is greater than 1, that means there's still a range of scales that's not affected by stratification in the flow, right? Which is analogous to your initial subrange in unstratified turbulence. So in our wake, this REB is decayed. Since I don't have this forcing, REB is going to go down, right? So turbulence is going to decay gradually. There's no surprise right here. And we have this Froude number horizontal. So I'm using the RMS horizontal velocity as my velocity scale, and the integral scale of the horizontal eddies as the length scale right here. So you can sort of think of it as the computation of two time scales. So n gives you the buoyancy sort of time scale, and the LH over U gives you the other one, which is the eddy turnover time in the horizontal direction. So, and the time series here shows that in this flow, right, this FRH is getting smaller and smaller, means the buoyancy control is actually establishing strongly in that flow. Right? It's getting smaller and smaller. So, so I'm going to focus on the 4 snapshots here and give you some qualitative understanding of the flow first. So, showing you the log 10 of dissipation rates. On the left, I'm showing you snapshots in the horizontal plane. And on the right, I'll give you the side view again. So you can see that dissipation is a very intermittent quantity, right? So even though you take the log of it, it's still getting, it's very intermittent, right? So as time goes on, you're having less and less dissipation in that flow. So the flow overall, again, it's out of balance. It's decaying, but locally, right? You see all those signatures of active turbulence, right? Could this be the result of SOC? Okay, so we're getting closer to sort of the methodology here. So I'm gonna assume that the SOC will occur locally, right? Just because overall the flow is out of balance, it's decaying. Right, so I'm going to say there's local cyclic cycles, like you see in the introduction of this talk, and I'm going to define a Richardson number that describes the larger scales in this flow. Okay, so if you think about an axis of length scales, right? I'm going to put a cutoff somewhere, right? So anything larger than this scale is considered to be large scales. Okay, so I'm going to try to construct a RI that describe the large scales. Okay, so I'm going to do that, show you how. And for this kind of length scale right here, I'm going to try to describe what the effective viscosity is. You know, this viscosity is what's applied to the larger scales right here, and has the same effects of the small scales that I will temporarily ignore in my analysis. Okay, and where do you think I should put this cutoff? So hinted at the Ozmidov scale. So based on scaling argument, it's the largest horizontal eddies that has enough energy to overturn. Okay, so so anything smaller than Ozmidov, you can think of it as not directly affected by stratification, and anything larger than that will be. So if I put a cutoff scale right here, right, you can say that if there's any self-organization happens in the flow, it will mainly affect the larger scales, and that's indeed what my RI and nu E will try to describe. Okay, so so I borrow lots of tools from the large eddy simulation community. So if you look at the sample spectrum right here, right? So you're going to put a filter somewhere. Right? That will be my Ozmidov scale. So if you look at the energy transfer, the energy equation for this energy budget equation for the energy that's contained in the filtered scale, you will see a term like this. Right? So this looks a lot like the shear production term if you look at the TKE budget, but right now I'm replacing that Reynolds stress with a residual stress that's due to the effect of the smaller scales. Okay, so and unlike turbulent shear production, which is typically positive, this term PR can be either positive or negative. Right, so I'm going to evaluate this PR quantity for locally for the flow and for different snapshots. And if I see a positive value at this grid point in my simulation, I know locally, right? So the energy is being transferred from large to small scales, and vice versa. Okay, so if it's going back, it's called an inverse cascade or a back scattering using the LES sort of terminology. And what people typically do if you were to do LES is to try to provide a closure for this tau IJR in terms of the sort of large scale quantities, right? So that's the whole point about doing LES, right? So if you do that, right, so you replace the tau IJ with so nu E times the rate of strain for the large scales, you get an expression of that, right? Again, if you're doing LES, you will have to model this, right? Because we are doing DNS, right? So we can take the DNS data and back calculate this nu E. Okay, and that's exactly what we did, right? So we'll take these two definitions of the PR and back calculate nu E as such, right? So same as PR, right? So PR can take either sign, nu E can also take either sign. If it's positive, then it's just normal diffusion we're used to. If it's negative, then that's the anti-diffusion. Okay, to give you some sense of this methodology, right? So on the top, you're looking at horizontal slice of the instantaneous velocity, right here. And this capital U, right, once I apply the filter, can be decomposed into a U bar, right? That's a large scale flow right here, right? It's just a blurrier version of the first one, plus the residual, the lowercase u. Okay, so I put, to go from U to U bar, I apply the filter using Ozmidov scale as half-width of the filter. Okay, so I'm cutting off the flow at this scale. That's the cutoff between the scales can be affected by stratification and cannot. Right. So what you have left in the residual is all those small scale turbulence here, and we're interested in quantifying the energy transfer rate and also the effective viscosity. Okay, so I'm gonna show you some snapshots of the RI. So again, this RI represents the larger scales, right? That's bigger than Ozmidov. So again, on the left, you're looking at the horizontal slice, and on the right, you're looking at side view. Okay, so you can already see that, right? So horizontal is this one right here, and the plan view, or the one on the right is a side view of it. So I play with the color scheme so that anything, so I'm plotting 1 over RI because it's easier to do that. If you see anything yellow, right, that means the RI value is below a quarter, so it's unstable, right? So if you look at the horizontal slice right here, you see lots of patches of yellow. That means within all those locations, right? So it's the shear unstable. Right? So RI is lower than a quarter, and they come in patches. Okay, so as so that indeed supports my hypothesis that there might be some local dynamics going on here because you can be unstable locally even though the flow is decaying with time. And if you look at the side view, right, you see all those structures that looks like layers but very short in the horizontal, in the streamwise direction, and eventually it becomes more organized and it looks like some local shear layers that's forming right here. And if I take the side view here on the right and try to compare it again with the field measurements, okay, so this is the RI from oceanic measurements, and anything warmer than this orange color is unstable. Right? Of course, this is the depth time diagram, and this is snapshots. It's different, but I don't think it's totally unreasonable to say that this is a bit similar to. Those two are quite similar to each other. So, okay. So, do we actually have RI clustering in stratified waves? So, I am looking at the PDF of this 1 over RI quantities and try to apply it to the 4 snapshots right here. You can see in the corner. So if I look at the PDF RI for the entire flow volume, right? So it doesn't really have that peak at a quarter that we expected, right? But if again, just following Smythe et al., if we conditionally sample the flow for the upper quartile of dissipation, right? So the top 25% in terms of dissipation rate, we do see that peak. very close to a quarter. And if I move forward in time, we go to this snapshot B, peak for upper quartile at a quarter, snapshot C at a quarter, D, right? So the flow has gone through decay for a while now. The peak actually moved towards the left. So R actually went up a little bit, but still quite close to a quarter. So again, I think I should convince you that this clustering seems to exist in this flow as well. And okay, so I went on and looked at some conditionally sampled dissipation rates in the flow, right? So again, horizontal axis showing you the 1 over Ri. So to the left, you have more unstable situations, and vice versa. So I'm plotting the dissipation. So basically, I go to the flow, right? I beat it up in terms of Ri, and just conditionally sample the dissipation rate for each bin I'm looking at. So this is a conditional mean of dissipation based on Ri for the 4 snapshots that I talked about. So you see 4 curves here, and you do see some familiar power law relation between the two. And I think for the unstable limit, right, this is just mixing a passive scalar. And for the more stable scenario, because epsilon is dominated by the vertical shear components, so in both limits, it kind of expects this kind of power law, which is great. And for panel B, I'm showing you this conditionally sampled epsilon divided by the volume average. Okay, and for some reason, right, so the curves collapse for the more stable regime, and I don't really know what to make of it. And I think oceanographers who tries to measure this volume average epsilon would be interested in this, but it's not central to our story today. So we talk about this PR quantity, which is energy transfer from the large to small scales. And this to show you some snapshots of that. Again, I'm cutting through the flow and give you horizontal slices. So PR, right? So red is positive, blue is negative. And you see some strong patches of either sign kind of sitting next to each other, which is kind of surprise to me, I guess. So if it's positive, then you know it's cascading forward, like conventional notion of forward cascade. And if it's red, it's going back, right? It's moving energy from smaller scales to larger, right? So you see these kind of patterns. And if I calculate the nu E, right? So this snapshot turbulence is not that active, but you see a nu E that's positive and negative, right? And it's comparable to the molecular values. Okay, some more conditional sampling here. So I'm looking at the energy transfer rate as a function of 1 over Ri. So for different snapshots, you see this upward going trend, which is expected, right? So as your flow is more unstable, it's doing more of the energy transfer. But I think the point of this plot really is PR is always positive. Okay, so because I'm plotting in a log scale, right? So no matter how stable your Ri is, right? So the PR is getting smaller and smaller, but it never drops below 0. That means overall the flow is still doing the forward cascade. Okay. Just based on that, I can do the PDF of the nu E here, which is the effective viscosity normalized by the molecular value, and I'm showing you the 4 snapshots here. You know, as the turbulence decays, right? See the envelope start to shrink. But if you look carefully, right, positive always wins negative by a little bit. Right? So it's decaying from the most wide envelope from snapshot 1, and as the flow decays, right, the magnitude of the nu E is actually decaying, right? But you always have a little bit more positive viscosity than negative, which I think is interesting. Okay. Is there a relationship between the eddy viscosity and Ri? which describes how stable the local flow is, right? So I'm approaching this in this phase diagram like that. You know, anything above this blue line, I have positive nu e. Anything below, I have negative nu e, means anti-diffusion versus diffusion. Anything to the left of this red line, I have stable scenarios, and to the right, I have unstable scenarios. And where do you think that distribution would be, right? I would confess to sort of a confusion that I had or still have. So, because I'm so influenced by this idea of Phillips mechanism for density layering, right? So if you have lower gradients, right, lower Ri, so to speak, you have a diffusive behavior and your left flank, so you are diffusion in a normal way. If you're on the right flank, you're doing anti-diffusion. So I guess my expectation before I saw my data, right, is that you will see lots of data points in quadrant 1 and 3, right, if you buy the Phillips mechanism. I don't know how many in the room will say the same thing, perhaps. So the data kind of surprised me a little bit, right? So you're looking at the joint PDF of the nu e, normalized by molecular, plotted against log 10 of 1 over Ri. Of course, I'm putting the magic number a quarter, putting here a vertical line to tell you where they are. So I guess there are several things you can say about this, right? So around this horizontal line, which corresponds to 0 viscosity, right? You see some sort of symmetry, okay? So, you know, there are almost equal positive nu e and negative nu e, which is a little bit surprised. And most of the flow is doing nothing. Okay, so around nu e equal to 0, you have the most probability distribution. So most of the flow is actually doing that. But for regions of flow that actually matter, right, i.e. you have higher magnitude of nu e, right, either diffusive or anti-diffusive, they tend to happen around Ri equal to a quarter. And is this a coincidence? So I'm going through my A, B, C, D again. So snapshot B. You know that flow is getting less and less energetic. That's why the envelope is shrinking again, right, compared to the first one. You still see all those important pieces aligning around a quarter. Another one, same thing. I shrunk a little more, right? But Ri here corresponds to the peak of the magnitudes. And D again. Okay, it does look like strongly stratified turbulence is doing something so that the most important events will happen around Richardson number of a quarter. Okay, I think I'm almost running out of time. 5 minutes left, and I think we do see some threshold behavior or clustering of Ri in this flow, and I hope, right? So shout out to Greg. You know, maybe this will be helpful for some of the models that you're developing. So I'll stop here and take questions. Thank you.
Yeah.
Yeah, I have a question on your filtering approach. Which type of filter did you use?
Gaussian.
Gaussian, okay. I'm just saying because there's an ample literature in LES where you do this a priori analysis and the amount of backscatter.
Yeah.
I'm saying backscatter, not inverse cascade, but backscatter. The amount of fluctuation you get depends on the filter. So if you do a sharp spectra, for instance, you get different PDFs. Yeah. So if you,
I can imagine that, but I think it shouldn't affect the sign of it.
It doesn't affect the sign. It's just if you're looking at the PDFs, you get much more backscatter with the sharp spectral than you get with the Gaussian filter. Yeah. The Gaussian filter has theoretical advantages as well because your subscale energy is actually an energy in the sense that it's positive.
Yeah.
So with the Gaussian filter, you should be fine.
Yeah. Thank you for that information. Yeah.
Yes.
Thank you. Very nice talk. So my question is that a bit specific one. But your production term, PR, is based on a kind of eddy viscosity type model, NUES.
Yeah.
So my question is that is there any possibility for the subgrid scale stress can be expressed in addition to such eddy viscosity type 1, you also have the additional contribution related to some kind of streak, vorticity, blah, blah, blah. So.
Yeah, so I think the reason why we pick this model is simple, as simple as possible. And you can, of course, be fancier and say, okay, so I want to maybe add some anisotropy in it, right? Because right now it's isotropic.
Because you are considering a smaller scale, like Ozmidov scale.
Yeah. So that's precisely why I put the filter there, because smaller than that, you kind of assume initial subrange and it's more isotropic than the bigger ones, which justifies the use of isotropic nu-E. Yeah.
Okay, but still, still depend on that type of model.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
So I had two questions, if I might. I mean, just since you bring out the pile and the self-organized criticality, one of the key features of all that is the concept of an avalanche, which is an extended propagating sequence of overturnings, which is distinct from the grain size, right? What is the avalanche in this story, or is there not a feature like that?
Economists here have to be careful because he's one of the authors. I think the avalanche in stratified turbulence is overturning.
Yeah, but I mean, do you see this? I mean, you should be able to filter the data, because this is done with data in other games, to look for kind of propagating events in space, right? The idea of an avalanche is it moves along, right, at an almost speed, a constant speed and all, and you can look for kind of tracks of mixing, if you will, or tracks of transport. Have you seen anything like that? It would require a different kind of filtering probably than what you've been doing, but it's seems doable, right?
Yeah, so for the two SOC papers that I cited, they look at the Thorpe scale, and it does follow a parallel distribution, and I think that's what they did. And I think
I'm talking more about space-time properties.
I think it might be challenging because it's a soup of dynamics right there, and I don't know if you can trace that space-time propagation that clearly. Yeah, it'd be nice to try.
The other question I had is if you drive it really hard, or you can imagine doing this is forced by the wind, right? So it's different than a gradient relaxation with a threshold and fueling, which is again the pile. If you imagine you force it very hard, why can't you drive the thing above Richardson number 1/4, right? I mean, if you do experiments with, numerical experiments with piles, actually, you usually get a profile that's under the critical gradient, and as you drive it harder and harder, comes up to the critical gradient and can exceed it, right? So, yeah, exactly.
I think, if you drive it over 1/4, then you don't get that clustering, and that's what this paper argues.
Excuse me?
So they try different sharing stabilities, right? So I guess the conclusion is unless you do humble, right?
No, but I mean, the control is the forcing, right? You imagine you have, you can crank up the wind as much as you like, never mind how much power your wind tunnel has, right? Why can't you drive it over critical?
I guess if you just keep forcing it, then it might go too far, and there's no way to come back to that critical state.
Yeah, but that's the point at some level.
Yes, that's certainly a possibility.
I mean, the argument would be there's some range of drive or forcing in which you get it and others when you don't.
Yeah.
There was one, yeah, in the back.
Yeah, thanks for a really nice talk. I was just wondering, so from like, I guess in your opinion, sort of how much of what you see would you say is consistent with this self-sustaining Phillips oscillation system that you sort of proposed, that regime diagram? You kind of showed some the distribution of these two parameters. I was wondering how much of the dynamics that you see can be explained by that cycle. Is there still something missing, or do you think that this sort of...
Oh, I think there's a lot missing here. And that's why I think you can help me here. I don't think I'm in a state to say for sure like what's happening between all those quadrants. Also, I have a data that shows you can be in all four quadrants almost with equal probability, right? But I don't see what's the detailed mechanism that allows you to go through the cycle. Whereas in a wind-driven process, I think it's clearer, right? Because it's out there.
You also kind of have another instability of the system in the sense that when you have a horizontal eddy, that thing has an associated length scale. Each horizontal eddy has its own associated vertical length scale, which is defined by that horizontal eddy. So I don't know if you've thought about how that factors into the generation of layers.
Yeah, I think a nice way to look at it is to build some reduced order model and try to figure out like how those pancake eddies interact and create like cycles like that. I like that suggestion. Yeah.
Yeah.
Yeah, I was wondering, the point is, if this SOC picture makes sense, it should be possible to write down a very simple reduced model, like the sandpile models of some kind, and just say, look, finally what's going on in here is that there's a threshold, you disturb it somewhere, can you write down a toy model? You can write down a sandpile-like model for this. And the other question is related to what Pat asked, is that in those models, you see full-scale invariance with no cutoff only if you drive infinitely slowly. At any non-zero driving rate, there's a cutoff length scale set by the driving rate, right? So can you comment on both those questions?
Okay, so reduced order model, I think I'm gonna read Greg's paper. I think it's possible to integrate some of the elements here into your model.
Perhaps.
I
I think you want something even simpler.
Yeah.
Okay. What's the second question? Sorry.
And the second question is just that, at least with all the standard SOC sandpile type models, the critical state is really accessed by driving infinitely slowly.
Yeah.
At any non-zero driving rate, you have a finite cutoff. And so for larger and larger systems, you actually have to drive ever more slowly. So is that seen it's related to what Pat was asking, is that seen in your model or in your studies or not?
Yeah, I think so. I think what's driving the secondary events that sort of keep turbulence alive is interaction of those pancake vortices, and they do sort of evolve very, very slowly. Especially in the strongly stratified, regime. I think what you said is true, right? So it's not contradicting the observations. Yeah, but do I know how exactly they interact? I don't.
Yeah.
Is there a perspective from, you get these negative values of effective viscosity if you imagine it was an LES? Are there versions that are there parameterizations you can create that involve, could you have a parameterized effective viscosity that gave you negative values some places that wouldn't blow the whole system up? Because you're sort of saying, if you do a DNS, there should be negative values, and mostly we don't assume negative values because...
We don't, because for numerical reasons, it's going to blow up, right? Yeah. So I kind of hoped that this PDF is a lot cleaner, so you can actually derive some scaling that you can use for your LES, but it's kind of messy, so, as you said, right, most of maybe LES model don't even care about the negative nu e, so.
Like, do you think there's hope for it being an approach that might work under some special regularity conditions, or is it just like a no-go?
Depends on where you put the filter or how much you resolve in LES. Right? So the place I put filter is Ozmidov scale, which is considerably smaller than lots of LES. So I suspect if you put put your grid at a larger scale, right, and you put a negative nu e, right, it's going to blow up your solution because it's kind of unphysical.
Final question by Alexi.
Yeah, I thought your comparison of your Richardson number, like layers to the Alford and Pinko observations is interesting. One of the weird things with that data set is that their overturns aren't necessarily always in the low Richardson number regions, right? Like they see
all those
some
black
overturns
dots,
like that, but others are more preferential to regions of high strain rate. And so I was wondering if you've looked at in your like DNS data where you get those overturns. Like have you tried to put the black dots on your plot?
I haven't, but that's an interesting idea. I'm going to try it. Yeah, I don't quite understand this either, right? So why the black dots, which is overturned, doesn't correspond to the
This
stable?
low Richardson number on its own in a complicated flow doesn't have that like theoretical backing. So
You're right. Depends a lot on how you average and get the RA as well.
You had one?
I have a question. So I think there is an analytical argument that when the Richardson number is less than a quarter, there will be Tobin-Helmholtz. Do you think that's relevant here?
Okay, so Miles Hubbard says necessary condition for sharing stabilities for a non-diffusive inviscid parallel flow is somewhere in the flow RI goes below 1/4, and what Alford and Pinko and myself is dealing with is fully turbulent flow. So whether you can sort of do that analogy, I don't know, but it seems to work, right?
It's just like the number is really consistent. So I'm just thinking about that.
Okay, so let's thank Ski again.